Okay, I hope everyone had a good reading week. Today we are going to start with concrete basics, or really an introduction to concrete. You've seen the way we go about this now, where I introduce the material, show you basic construction practices, show you some sizing guidelines, and then the second week we focus on the actual design process. Concrete's interesting because to talk about concrete design, it's actually, as much as it might have been the one that we've been using the most, or the one that was maybe almost done blindly the most, for having real scientific capabilities, it's the one that's actually the hardest to do calculations on. Mostly because there's a few things at play. There are multiple materials in it, so in that respect, it's not isotropic. It is a non-isotropic material. It's also a composite material in two ways. The concrete itself has sand and rock in it that bind together. That makes it composite. The rebar, or the steel inside the concrete, then also has to bind with it in some way to become composite. You guys don't really know what composite means yet, except you've heard me talk about it a lot. You've heard me say it makes two things act together. And so next week, when we talk about design with concrete, we're not going to go too much into the math behind it. I'm going to talk about the principles of how we design with concrete, but I'm going to spend a lot of time talking about composite and why composite, if you can make something composite, is really pretty amazing and the benefits we can get out of it. So that's what we'll focus on next week. This week, I'm going to follow the same pattern I did for both steel and wood, where I introduce the material and show you basic kind of low-key sizing methods for it. What you'd put on preliminary drawings, for example. So you should know what basic concrete beams look like. So this is a concrete beam. The concrete bars would act in compression. So if we had a column, these bars, or the concrete itself, would be doing the compression work. You can use the steel in compression as well, and I'll show you that next week. But the concrete does a lot of the work. The steel helps to stop the concrete from bulging outward. In tension, concrete has almost zero capacity. In fact, for design purposes, we say it has zero capacity. So the steel has to do all the work. And shear is a combination between steel and concrete. And we'll go more into that next week. But I just wanted to start showing you an image and start associating the terms with the different component in the section. But next week, we'll really look at why the concrete is compression, why the steel rebar is tension, and why the concrete and steel does the shear work. Reinforcing or reinforcing bars, we often colloquially refer to them as rebar. It has an Fy of 400, which is different than what our normal structural steel was. E stays the same, 200,000 MPa. And then we give names to them. So 10 is really saying it's pretty darn close to 10 millimeters in diameter. 25M is pretty darn close to 25 millimeters in diameter. And here are the cross-sectional areas that we often say those bars have. 10M bars are really, really floppy. We don't like to use them as the main reinforcing. We'll use them to tie things together, for example, but to use them as the main reinforcing, they're really, it's almost hard to pick them up because they bend. And if they are the main reinforcing in something, you can't step on them because it'll bend them and deform them. We tend to space bars apart at about 2.5 times the diameter, this symbol representing diameter. We're up to 500 millimeters, or we might do it 3 times the thickness of the wall or slab. Usually less than that. That would be an upper bound of it. So a minimum of 2.5 times, that's to allow the concrete to flow down in around the bars. Usually fewer larger bars is the cheapest way to build things, but smaller bars work better. But if you go too large, it actually gets really, really expensive. So 45 and 55 M bars, really, really expensive. We probably work the most with structural elements, 15, 20, and 25, and 10 M bars being for the ties. The concrete strength we actually refer to as F prime C. So remember, it's the compressive strength of concrete. The prime means that we've done some stuff to it in our calculations. It's a idealized curve of it. So don't worry about it too much, but you remember steel we called Fy, and that was the yield strength of the steel. Concrete, we only count compression because we say it has zero capacity and tension. So compression, and it's brittle. So it is an ultimate capacity. It is the limit of what it can take. We have no ductile zone. Concrete is brittle. So footings and caissons would use 20 MPa. Foundation walls and a slab on grade, we might use 25 MPa, unless it's being exposed to de-icing chemicals, and then we'd bump it up. Framed slabs, columns, mid-rise, high, and high-rise columns, we start to go up in strength. These levels of strength start to be really expensive. My understanding is it's not that much of a cost implication in that zone. There is some cost, but not that huge. We add water into our concrete to make it flowable, so we have a water-cement ratio that would be specified that contributes to the strength. And then we have entrained air, or tiny little air bubbles inside our concrete. And that affects its workability and different strength requirements and its performance in different environments. So a structural engineer will put these elements on the structural drawings, but the mix designer or the concrete plant is ultimately responsible for this. So they take the information from the structural drawings and produce a mix design from that. So stress strain curves, remember I love stress strain curves in exams. You should have a basic understanding of what the stress strain curves look like for steel and concrete. Wood was just a brittle stress strain curve. I didn't even show it to you, but you should be able to interpolate that or figure that out. Concrete, this is concrete on its own in compression, where we have an ultimate. And reinforcing steel, where you can see that it is ductile. What we really care about is a weird combination of these two. So I will show you what a stress profile of steel and concrete or reinforced concrete beams look like next week. And knowing what those stress profiles look like is really interesting as well. So I'll make sure I show you that next week. Those slides that we just did, I'm going to re-show you next week as well, just as a refresher and a reminder, because we're going to talk more about those things. So now let's talk about the advantages and disadvantages of concrete. Some of them you've heard me talk about a little bit, simply because they were in contrast to the other materials. So concrete is very adaptable in the construction phase. We can make it to almost any shape we want. We physically make it, almost like Play-Doh or clay, so we can do really unique, interesting shapes with it. You saw great concrete work come out of the 50s and 60s. The reason that is that at the time, and you've heard me talk about this before, is that labor was very cheap and materials were very, very, very expensive. So we did everything we could to limit material, even if it meant more labor hours had to be thrown at the problem. So to get rid of material, we would form these beautiful sculpted shapes that looked like they were purely for aesthetics, but they were actually very structurally specific, and they followed the path of where we needed our capacity the most. So we would really throw concrete, or we would do whatever we could to take concrete out and only put it at the parts where we needed it the most, even if it meant more labor hours. In today's market, you see concrete construction looking rather bland and boring. Well, that's because labor is really expensive and material is really, really cheap. So if it saves labor to just make it one straight element, even though it has more material than we might need, it's the more efficient or the cheaper way to build our construction. Concrete has a short lead time. You can have somebody win the project and they can start mobilizing on the site almost immediately, assuming they have all their permits. They can probably get out there very, very quickly. We end up with a shallow depth of structure, and you've seen me draw this before, but I might as well draw it again, where our floor plate for concrete, sorry, I am drawing something here, I'm not just disappearing on you. I've drawn my deck spanning the wrong way. This was more to just to visually show you something. So you can see our concrete slab replaces deck and joists. So they are both doing all the same work. They'd span to beams or girders, but those two things are quite often interchangeable. Concrete, we have the same mass uniformly, or the same depth pretty much everywhere. Our concrete on metal deck on open web steel joists might be shallower locally, but we have to come down around these joists. Now, depending on what your needs are, I can't tell you which one is better. If you have ducts that go like that, it might be very helpful to have it run in between the joists versus having that same decked underneath. You can see it drops it down. But if your ducts are running in the opposite direction, you can see that having this concrete slab might be beneficial to your project. So it's not always clear which one is the better option. We might start to see patterns or where our choices might be kind of just set out because we know it's cheaper because we've built a bunch of them in the past. Concrete makes a beautiful finish. If you can do really good formwork, you've almost got your finish built in because it is non-combustible and has a good fire rating. We don't have to hide it away if we have non-combustible criteria or high fire rating criteria. Steel structures can be very beautiful leaving the steel exposed, but if we have a high fire rating requirement, we might need to hide it away simply because we need something to guard the steel against the fire. Wood is a very, very beautiful finish, but if we have a non-combustible criteria, it doesn't matter. We have to hide it away or find some way of preserving it to be protected from the fire. Concrete can be very good acoustically. It can, as much as I told you, concrete is brittle, and it is, the concrete itself is brittle. We have ductility listed as an advantage. That's because we have that steel inside our concrete, and we know steel is ductile. Are you going to your meeting now?
Getting a coffee. Go
Yeah, it would be my fourth this morning, but I'd really like it anyway. I'm going to be vibrating by the end of the lecture. We put the steel inside the concrete, and if we proportion it properly, we can end up with a ductile element. Even though the concrete itself is brittle, the steel can be responsible for the ductility. And we used to barely think about that because as long as it was strong enough, it didn't matter. But in places with high seismic criteria and high seismic zones, ductility is essential in kind of long-term performance and preservation of the building in a high seismic event. So for high seismic zones, if you're building with concrete, it is a very refined process to get that steel quantity just perfect. Having too much isn't necessarily a good thing. You can actually make things behave badly by having too much steel in things, in concrete elements as well. So it's a bit of a fine-tuning act to get that just so. Concrete has great corrosion resistance. Now, any of you who live in Toronto and have been down under the Gardner and see spalling of the concrete or chunks of it falling off would be like, you cray, girl. That concrete is not corrosion resistant because the salt comes down on the concrete deck, it kind of works its way through, the rebar rusts, it expands slightly, and poof, off pops the concrete at the bottom. But what you have to remember about the Gardner is that it was built, they were planning for 30 years, but they were accepting 50 years, and we're at what, over 70 years now of the Gardner being in service? Like, it's way past its expected life expectancy. And it is still strong enough and functioning. It looks like crap, but it does need work. So there is lots of repair happening to it. But that is an example of a corrosion-heavy environment for concrete, just due to all the salt and the chemicals that are put on it, and it's held up well past the life expectancy it was expected to have. Disadvantages. Concrete cannot span that far. It can span far enough, and it works really well in certain applications. You know what? There's another one I'm going to put on here, and I'll add it when we get to it. It is heavy, so we've got weight here, and that weight can start to limit the spans. You have to add more concrete to make it to be able to span farther, and pretty soon its own self-weight can be the thing that keeps it from working. I've actually had projects where we were doing renovations, and they said, oh, well, we'll just add more concrete on top. But in fact, to have the bottom steel work the way we needed to, we just couldn't add the concrete we needed to. The weight of the concrete started to be the problem. Alterations are a pain in the butt in concrete. If this is our wall, and we want to add that doorway into it, if this was a steel building, I was going to accuse you of stealing my blue pen, but you didn't. Now I feel like a bit of a jerk. If this is a steel building, well, we'd know exactly where those elements were. We could even kind of open up the wall and see the steel without damaging it, and we'd know exactly what was the crucial structural elements, and away we would go. If this was a concrete building, that doesn't show up very well. This is a concrete building, and you're going to see this in the pictures in a little bit. That is all of our structural element. So how do you know if you can take that component away? And I think I told you guys this story already, but I'm going to tell you again just because it's a really good story. I was doing a project renovation exactly like this in High Park, and the contractor was like, yeah, we want to put a doorway in it. We just want you to take a quick look at it. We're sure it's fine because, and I'll draw you a plan of what this building looked like, and I'll draw in the reinforcing walls in it. And they had a core, and then they had a couple walls going in the other direction. So if this is a plan, all of the red is the concrete shear walls, and they wanted to put a door opening right there. So in the direction that had a gazillion shear walls, they wanted to put in a very small door opening, not at the end of a wall, so kind of in a spot that worked the best. And just visually by inspection, no problem, it worked. The building department, because remember, earthquake loads, same in both directions. I did do a check for wind. I did do some math checks. But visually by inspection, that works. I looked at a ratio of what wall was being removed, and it was less than 1% of shear wall was being removed. Again, no problem in my mind. I then did some quick numbers and looked at it and did find that it was no problem. The building department, sometimes you get one particular person who's having a rough day, and that particular person at the building department said we needed to do a 3D analysis of the building to prove that it had the capacity to have that door put in it. I wrote a memo saying that I disagreed, because that's redesigning a building. That is taking a building that's already built and redesigning it when we can see that we're doing almost nothing to this building. Now, don't take this too much to heart, because there are times where you do need to go further and do the math. But this one was so visually obvious to a professional in the industry that there was no problem, that I wrote a memo saying we didn't need to do that. I signed and stamped it, and I said we were removing less than 1% of the wall. They came back and said we did. The poor owner, they now had to hire some. I can't do it for free. I mean, I would love to, but it's not up to me to make that call. And so they needed to pay me for my hours. But what an added cost to the owner to now have to pay somebody to re-engineer the building. So I did it just to prove it. They wanted proof, they wanted documentation, so I provided the documentation, but I also wrote maybe what you might call a scathing letter, because often when we're talking about metric versus imperial, we might call a 200 wall 203 or 200. Just that 3 millimeters of thickness difference in the width of the wall is kind of peanuts. And one engineer might say 203 and one might say 200. We consider it such a small difference that it's almost irrelevant in the design process. Removing this wall made less difference than using 200 versus 203 in the wall. So I wrote a memo and sent it to that poor building official's boss. I was having a day. I think I was pregnant at the time. I think I was pregnant with Malcolm. So I might have been a little bit fired up about it. But on the owner's behalf, I felt that it was an important thing to do, to just stand up and say, no, this didn't need this in-depth analysis. That's somebody blindly following software instead of the rational capabilities of an engineer to problem solve. So, yeah, alterations. You could end up with that kind of problem. This is a big one. The construction is sensitive to weather. If it is bad weather, you can... if it is a really, really cold winter, you can actually end up having to stop construction completely. Just full stop. It's too cold to pour this concrete. Really hot days can be detrimental to concrete pouring as well. There was a winter, I think it was 2012, 2013 winter maybe, that we had just absolutely record-breaking cold weather. And I was working in an office at the time, and beside us they were building a concrete building. And they were going along like gangbusters. They were building it. They got up to the 3rd floor, and that winter hit, and construction stopped. It basically stopped all winter. It was too cold to pour the concrete. So there's a risk involved there. The next winter, we had the mildest winter ever, and so concrete construction just went like mad. It didn't stop at all. I think they lost like 2 days all winter. So really, we can't predict the weather, so you pay the contractor to bear that risk. Quality control. Steel, we have great quality control in the plant where they're actually making the steel, because we have chemists looking at the chemical makeup of it. And then when they're rolling it, they have machines rolling it to a very fine precision. And then when it's being erected in the field, we can go look and see very easily if things don't match what we expect it to. You're going to see some images of concrete construction in a few minutes where the rebar is doing the work, or a chunk of the work. There are, instead of a few big pieces of steel, like in steel construction doing the work, there are a gazillion small pieces doing the work. And each one is critical. Maybe not as critical as that one big piece is, but it's a lot harder to kind of see that what was requested on the drawings is carried out. The concrete itself is somebody in a parking lot throwing a bunch of stuff into a back of a big truck, and it literally mixes itself on the way to the site. It is at the mercy of a rainy day, a hot day. Were they hosing it down? What other construction was happening on site? All of those things can help impact the quality control of the concrete. So as an engineer walking onto site, I can't look at it as easily and say, this perfectly meets what my contract documents set out to say. And I already touched on weight. Now, there's another one here that's not on this slide, and I'm gonna add it in. This is slide 6. I'm gonna add in build it twice. So the disadvantage of concrete is that we build it twice. First, we build a fake wood building, and then we pour liquid concrete on it until it cures, and then we can take the wood away. Now, the best thing about concrete is we can reuse that wood to build the next floor.
Yeah.
Thank you. We can reuse that wood to build the next floor. So where it starts to be economical is in the ability to reuse that material. If you are building 4 floors that are almost identical and you can reuse that wood building, well, each floor costs a quarter of the wood material because you're using it 4 times. If you're just building 1 floor, you're paying for all that formwork for 1 floor, for 1 use. So that can mean that concrete's maybe not the most economical for a low-level element. A low-story element when I say low-level. So where is concrete used the most? Good concrete. Good coffee, Bowick. So let's take a look. What are some good concrete applications? That was a really slow, weird entry, wasn't it? Mid-rise apartment buildings. Well, the reason they're good is they have short spans. Living spaces often don't have huge rooms. It's actually almost uncomfortable to have 12-meter long rooms. So 6-meter spans, which concrete's really kind of great for, is perfect for concrete. It also usually has the same floor plate, 5 to 15 times, which means we get to reuse that formwork 5 to 15 times, which makes it really cost effective. So the same deal for office buildings. Parking garages, it's just great because of its durability. We have something, even though it's not nearly as strong as steel, it's pretty strong, and we have it everywhere, versus concrete on metal deck, which you could imagine trying to hold a tire in between the joists, whereas with a concrete deck, we have that material on every square inch of the building. Foundations, same reason. We have something everywhere. So if what we're trying to do is hold back something that's everywhere with high loads, and we're going to see, or we saw when we looked at soil loads, just how heavy those soil loads can be, especially when they're trying to push in. Having concrete absolutely everywhere around the perimeter means we have something strong enough everywhere around the perimeter. And then concrete can be great for unique structures. That's because it is so versatile. We can form it into almost any shape that we want to. What really affects the cost? And this is the same thing. Oh, I do say it there. So, in the cost, the formwork is probably one of the biggest costs of it, because we have to, put it in, we have to pay for the material, we have to install it, and then remove it. The strength of the concrete, long spans. Long spans mean a lot more rebar and a lot more work, so it increases the cost. Loading is pretty linear, but as you have higher loadings, you're going to increase the cost. A big one is the time of the year. If you have a schedule that demands the concrete work mostly be done in the winter, you're going to pay for that heavily. So let's take a look at our sizing guidelines. This is a relatively short, relatively short lecture. I'm just getting my trusty blanket. A relatively short lecture, but I think you guys deserve it. You guys were fracking rock stars at the beginning of the semester. So now we kind of get to lay back and relax as you probably come into the intense time for some of your other courses. So as much as I touched on hollow core, did I touch on hollow core when we looked at steel? No, we didn't. So maybe I did. Anyway, regardless, it's a good time to talk about it right here. So hollow core would replace concrete deck and open web steel joists. I feel like there are notes that I had in here that are missing. So it replaces open web steel joists plus deck. So anywhere we would have had the combo of open web steel joists and deck, we would put hollow core in instead. Now hollow core is really acting like a bunch of small little beams. So if this is a cross section of our hollow core deck, so you can see that we've got these concrete panels that have these extruded holes in them. If it looks like that, what we're really saying is we've got a series of beams that are so close together that they're working together. So, look at that. Doesn't that look like one of the like a little I-beam? And so we're doing that same philosophy. That stuff in the middle isn't working as hard. In a cast concrete slab, we have all this extra weight that's not doing that much work for us. So the idea of hollow core slabs is it takes out that material that wasn't doing as much work for us. But now it is a more refined process that's being done in a shop that has a bit more cost to it. So the hollow core becomes really cost effective if we are doing it in a project where we have a lot of repetition or a lot of the same thing, because it is made and engineered by the fabricator. So me as the base building engineer would figure out what my loads were, I would figure out my span, and then I would go to load tables and pick out the exact correct slab. And then they, as the fabricator, would also engineer it in the end. So it comes in a variety of depths, 150 all the way to 350, but 200, 250, and 300 are the most common. Our sizing guideline is the depth equals L divided by 40. So let's take a look at one here. If the beams are at 800 or 8,000 millimeters center to center, 8 meters, what depth of precast should we use? So we've got our 8,000 divided by our sizing guideline of 40, and that gives us 200. Well, that's pretty bang on. That seems to tell us that 200 thick hollow core slabs work really well at 8 meter spans. So again, I've listed it here again. You may see it listed in Imperial at 152, 203, 254, 305, and 356. And different manufacturers make them different, whether it's the exact dimensions of Imperial or exact dimensions of metric, but you often look at the same sizing guideline no matter what, the same loading tables no matter what. So if you have every millimeter counting in your headroom, you need to know if your supplier is making it metric or Imperial. So when would we bother with these other weird dimension ones, or the ones that aren't that common? Well, that would be if we have, maybe we have a floor plan, maybe we have a floor plan that looks like this, and we have (200) slabs. Actually, we'd probably even use 200 slabs there. But maybe we have a project that there's one room with tight headroom and we need something special and we already have hollow core on the project. Well, that's where we might use 150. Or we have a spot that has really heavy loading that we might use the 300 or the 350 very specifically because we don't want to then switch to a different material. So we don't have to penalize the whole project by being at that higher dimension. So most of the project is at that dimension, with a few low-key spots having a heavier or the thicker dimension. So what's optimal for each depth? A 200 hollow core slab, well, we can just reverse this equation. 40 times 200, an 8-meter span seems pretty good for 200 hollow core. 250 spans about 10 meters, and 300 spans about 12 meters. And so those are, if you're working on a project with 10-meter spans, or 9-meter spans even, you probably want 250 hollow core. One-way slabs. So a one-way slab is when it's like our concrete is working the same way as our hollow core. So our slab is acting like it's spanning in one direction. It's got a support here, and it's got a support here. Our sizing guideline is L divided by 18. It's custom made, so it could be whatever dimension you want, but we typically talk about it in increments of 50 millimeters. That's just standard. You would rarely put something else on a drawing. It would have to be a highly custom thing or highly specific. Normally we'd be talking about 200, 250, 300. So how deep does a one-way slab need? How deep does a one-way slab need to be if we're spanning 4 meters? So our sizing guideline, L equals 4,000. Our sizing guideline is 18. That gives us a depth of 222 millimeters. But we would say that that was a 250 cast-in-place concrete slab. We would bump that up to the next closest dimension of 50. So if 200, 250, and 300 slabs are typical slabs that are formed in Ontario, how far can they span as a one-way slab? 200 slab can span about 3.6 meters, a 250 slab can span about 4.5, and a 300 slab spans about 5.4. Well, you've heard us, or you've heard me, and probably other people say that concrete works really good at about a 6-meter span. This seems to say otherwise, which makes it seem like I'm full of it. Here's the thing. Our concrete grids are often pretty darn close to square. They might be slightly rectangular, but they're pretty darn close to square. And if they are within a rectangular range of 2 to 1, meaning the long side is no bigger than twice the short side, we can say we have a two-way slab system. I feel like I should draw a picture of what a two-way slab looks like. And add it into the slides for you. So I am going to add one of those in for you guys. So I'm going to add that to my notes of things to add. One-way versus two-way. I feel like I always end up drawing this, and it's just dawning on me that, hey, maybe I should make a slide for this. So the real advantage in a two-way slab is if this is our slab, and we have beams all the way around the perimeter, and maybe we have some columns. We have our load going to the different edges in a triangular pattern. So instead of taking half of this whole area, each beam is only taking a quarter, and it's in a triangular distribution. As we get to that longer profile, we still get to make those corners be at a 45 degree, but if we end up with our profile being longer than 2 to 1, so you can see the long side is more than twice the short side, we'll look at the tributary area that's loading this beam. Yeah, it's got a little bit less here at the ends, but it still looks pretty darn similar to a one-way slab loading outline there. So if the ratios are more than 2 to 1, then it is a one-way slab. You can call it a two-way slab, but it won't be true. It will be a one-way slab. If you keep it closer to square, it can be even slightly square. Hi, buddy. Can be slightly longer in one dimension. Then you can use the sizing guideline of a two-way slab. It means you have to have, hi, buddy. You have to have something that can support it there, though. You actually have to design a beam there now to pick that up. So the ratio has to be correct, and you have to have something there to pick it up. But if you've met that criteria, well then you can use a sizing guideline of L divided by 30. Most of the concrete buildings we do in Ontario happen to just have a great framing layout that allows us to use two-way slabs a lot. A 6x6 grid is pretty common, maybe 6x8, but you can see that we're still meeting that kind of grid layout. But you have to remember to use the larger dimension as your length. Typical sizes, it's still the same framing work. So 200, 250, and 300, the most common sizes. So how deep does a two-way slab need to be if we're spanning 8 meters? 8 divided by 30, 8,000 divided by 30 equals 266. So we'd bump that up, or we'd round that to the next 50 millimeter increment, and we'd have a 300 cast-in-place concrete slab. Again, 200, 250, and 300 slabs are the most common ones in Ontario. So we would say we have a 30 by 200, so the sizing guideline of 30. A 200 slab can span 6 meters if we have that framing network that we need. Hi, buddy. What are you doing? Oh, are you building a spaceship? A 250 slab can span 7.5 meters. A 300 slab can span 9 meters. So you can see these start to look like the economical ones that we talk about being often built in Ontario. Again, though, you have to make sure you give it the support you need for a two-way slab. You have to make sure there's beams around it if you want to use these sizing guidelines. Concrete beams. Concrete beams, if it is just a regular old beam picking up some slab, well, our sizing guideline is length divided by 16. If it's working hard, meaning that there's a point load on it or something extra happening, it would be length divided by 12. Our beam width, I hate width sizing guidelines. You've heard me say this again and again and again and again. This is more, there is absolutely no truth to this whatsoever, but it lets you draw something that looks pretty good on the drawings. So take nothing to heart with this. In fact, I'm gonna put an asterisk on the width one, saying for drawing. Mostly because we can have really long, or we can have really wide flat beams too. The really cool thing about concrete slabs is they can be part of, the really cool thing about concrete beams is they can be part of the slab. So if we have a concrete slab and a beam, take a look at this cross section. We have the depth of our beam included in the depth of our slab. So if you figure out that this needs to be 600 and that's a 200 slab, well, you only need a projection of 400 in there. You can actually cast the top part of your beam into your concrete, which is really nice. We can also sometimes even take advantage of that mathematically. It depends. We don't often do it simply because it adds a lot of kind of rigor in the check work, and we've already talked about how inspecting rebar is probably one of the hardest parts of the project. So we tend to make it as obvious as possible, or as visually obvious as possible, but we do have some options there as well. Oh look, I actually used an example of 200 and 400 in a 600 beam. So concrete beams, what depth below the slab do we need for a beam spanning 9 meters if the slab is 200? Well, our sizing guideline says L divided by 16. So our sizing guideline gives us 9 meters divided by 16, or 562.5. We would never frame that. We would round that, especially for a preliminary sizing guideline, for preliminary drawings. We would bump that up to 600. The beam projects 400 below our 200 millimeter slab. I've said it's 200 millimeters wide here. I don't like even putting that there. I might even change the width on slide 15 with a note, just so you guys don't rely on it thinking that it is kind of set in the world as a thing that is true. It's mostly just to give you something visually nice to draw there. Walls, columns and walls. So concrete columns, and this is for a column, it's the smallest dimension needs to meet this, would be our height divided by 200. So they're custom made on site, typically in 50 millimeter increments, but not required. We would often do it though. So for anything I'm asking you, I want you to round up to the 50 millimeter increment. Walls wouldn't tend to be less than 200. You wouldn't do it because it's hard to form, it's hard to get your rebar in. Maybe if it was short and lightly loaded, or a feature where you have people lending special care to it and really focusing on it and making sure that it is built exactly the way it needs to be structurally, then you might do it. So I've done 150 walls as a feature where everybody is aware that it is the unusual thing. So lots of extra efforts put into it. So what would the size of the columns in a wall and walls be for a building with a 4.2 story to story height? So our height is 4.2 meters. Our sizing guideline is 20 or 25, depending on if it's a column or a wall. So our column is 4.2 divided by 20, or 210, and our wall is 4.2 divided by 25, or 168 millimeters. So our columns, the smallest dimension would want to be 250, so maybe a 250 by 250 column. And our wall would want to be 200 millimeters thick. Well, 200 millimeter thick walls are pretty common in concrete construction above grade, maybe 250. Now, here's the thing. What if that column was on the ground floor of a 45-story building? What if it was on the top story of a 45-story building? Well, that 250 by 250 seems to make sense. But the bottom story is carrying 45 times the load of the top one. This doesn't seem to make a lot of sense anymore. And this is where sizing guidelines fall apart. And you understanding the kind of scope that your building is in is really advantageous. You know intuitively that that same column wouldn't work in both spots. So this sizing guideline would probably work, in the 4 to 5 story range. Maybe you need to double it as you get past that. So if I said 5 stories, and this is legit off the cuff, so 45 divided by 5 is 9 times 250. So 250 times 9, well, maybe you need a 2 meter by 2 meter column. I don't know, but I'm just trying to give you an idea of what you need to draw on a set of drawings. Maybe it's going to be 1 meter by 1 meter, but it's going to have a frac ton of steel in it, kind of doing some work in there. So be aware of when your thing is doing something extraordinary, or what you're designing is doing something extraordinary. These sizing guidelines are just about trying to give you something to draw in your drawings at a very early stage that looks like they make sense. So there's no real place to give you masonry sizing guidelines, so I wanted to make sure I threw it in here. So we have two different criteria for masonry. Now masonry comes in 190 thickness, 240 thickness, and 290 thickness. 190 is the most common. We use 240 sometimes. If it is brick, there'd be more than one wife. So there'd be multiple pieces stacked together with one turned inwards every so often, tying those two stacks together. The non-load-bearing walls, the load-bearing walls are H divided by 20, and the non-load-bearing partitions are H divided by 36. There is a difference in how we detail them. If you have a non-load-bearing wall, you have to make sure it can't bear load. So at the top of our building, we have to do something to make sure it can't bear load. So if we had masonry with metal deck, say, if it was load-bearing, it would come up and touch the underside of the deck. If we need it to not load-bear, we know that that deck is going to move up and down. But we also know that we don't want our wall to tip over. We need to brace it using the deck at the top. So what we do, and you guys have this, I gave you guys typical details early in the term. Typical details were uploaded to Quercus, but you can see here what we would do is we would build our non-load-bearing partition. We would put a clip angle here with a slotted connection. So this deck with this angle could move up and down, and then if you needed to make sure there was a fire stop, that would be some sort of squishy, compressible material that makes sure fire can't cross that barrier, but that the deck can move up and down and not put load on the block. So what would be the size of walls and partitions for a building with that same 4.2 story-to-story height? Well, our load-bearing walls, the sizing guideline is 20, and non-load-bearing walls, our sizing guideline is 13. I'm gonna put a drawing on that last page too of image. So our load-bearing wall is 4.2 meters divided by 20, or 210 millimeters. We would use 240 block. Our partition would be 190 block. So for a 4.2 story tall height, we would use 240 block and 190 block for load-bearing and non-load-bearing masonry walls in the building. This is just because it always comes up, and a lot of architects don't even know this, and it's just kind of nice to have it handy. If you have a brick veneer, so it is not load-bearing, and it is being connected back in some way to stop it from tipping over from your building, so you have maybe you have metal studs, maybe you have a concrete wall, you have something here that is your structure, and then you have a brick veneer on it. If it is sitting on the concrete foundation, you can go up to 11 meters tall, which is pretty tall. If it is taller than that, you have to have shelf angles story to story. I think I might even add some images of that. But basically what we're saying is if it's sitting on a foundation wall, you've got a block wall and a masonry veneer and a concrete foundation. And these are tied together laterally, periodically. If you are at some other story dimension and you've got your load-bearing wall, we would have We would have our load-bearing wall here. We would have our brick veneer that stops at the storyline with a little shelf angle that's attached to this here. But we'd still tie the brick back periodically just to stop it from tipping forward off the building. But the gravity load would be carried on that shelf angle. So brick veneer is laterally connected to the building every 600 millimeters. So let's look at some typical construction now. I said this is going to be a nice, short, easy lecture. So now we get to sit back, pop some popcorn, and take a look at some basic images. So look at this. We've got a one-way slab. This is a parking structure. So the lowest level of architectural concrete you could imagine, and it's still pretty darn nice. But you can see you've got some seam lines there. That might be even an expansion joint they've got. You've got round columns here. You can see that the formwork was kind of cardboard that went around in a circle. But the big thing here is we're looking at a flat plate. Here is a flat plate with drop panels. Concrete actually behaves very poorly in shear. Most of our other materials, we haven't worried too much about shear, but concrete doesn't behave very well in shear. And the worst part of the shear is where the slab gets close to the columns. Imagine holding up a pizza on chopsticks. So you've got a pizza on chopsticks. You can imagine that hot pizza sliding down around the chopsticks. Well, that is essentially what a concrete slab wants to do. So what we do is we put reinforcing or an extra bit of concrete where that slab wants to drop down around the column, which is why they're called drop panels. Sometimes even that's not enough, and we might put a flat plate with drop panels and capitals on them. So that's where really our shear is the heaviest, and we want to make sure that that slab doesn't shear down around the concrete column. And I showed you a failure of that, I believe in the very first lecture, that I showed you kind of that was a key failure method of slabs. Here are some drop beams with a one-way slab. You can see that it's a long, linear direction with no supports in that direction, so the only way the slab can span is from here to here. We can't get a two-way slab out of this. It was impossible to find an image of a two-way slab. Actually, you know what? This is probably a two-way slab. It doesn't look like it because where the heck are the beams? This one too. Where the heck are the beams? But what's really interesting is that if it is lightly loaded enough, we can actually put our beams right in our slab. So if that is our plan with our columns right here, what we can do is in our kind of web of normal reinforcing, we can heavily reinforce in the slab locally. So sometimes we can get away with that, and we don't even have to have a beam projection. So you can see the blue is the litter of normal reinforcing we would have in there, and then the red is the cluster of reinforcing that would be acting like our beams. So you can't see it, but there's beams in there. Waffle slabs you saw a lot in the 50s and 60s because, again, the formwork was really expensive, but it was way cheaper than having that material in there. The labor of putting in that formwork was still cheaper than having that filled with material. We now are in an economy where filling that with concrete is cheaper than trying to form that there. So the labor of trying to make this happen is way too expensive. We're kind of at a cusp of changing even again what that economy dynamic is in our construction methods, and we don't even know because we're on like the cusp of something very unique with sustainability and kind of you know, just environmental thought considerations in how we build is really changing things. Not that common, but you can see here there are purlins and a beam coming to a slab, or to another beam. So a slab, purlins, beams, columns. I've never designed this. I've never seen that happen here, but it's just interesting to see that you can make concrete mimic the ways we're used to seeing things designed. Here are some beams with a one-way slab. So you can see some deeper beams with a one-way slab here. But you can see that this ratio is bigger than 2 to 1. So even though there's a beam here, it doesn't matter because it can't pick up this slab. My guess is that this beam is actually a girder picking up this beam right here. Oh, look, I did find a two-way slab. But I could only find a crappy image of it. So I'm going to change the order of those because I don't like the order those are in. They should be switched around a little bit. So around 25 to 28, reorder. Concrete shell. Concrete, because we can kind of form it into whatever shape we want. You can make some beautiful kind of forms out of it. It's, Nervi and all of those people that like these glorious, beautiful, expressive structures that, it followed the function, the form followed the function. Really were possible because labor was cheap and material was expensive. One of the things to think of when you're doing a shell, look, it wants to kick out. It's the same thing we saw with steel. So our reaction here, we need something to stop it from kicking out. Well, what they did here was they put another shell. So one's pushing this way, one's pushing that way. And eventually you'd get to the end, if it was a bridge, for example, you'd get to the end and have to deal with it. But they solved it by this being a circle, so it always just starts to push against itself. Here's an image of some hollow core being installed. Kind of the panacea I talked about with hollow core is that, we can use these flutes to run our air system through, our mechanical will run through, it'll be glorious, we're going to save all of this stuff. The reality is any project I've ever seen that talked about, it can't happen. Look at where these flutes are supposed to run through to each other. This is how the hollow core sits on a steel beam. They have to tie these together so that as they deflect, they don't get cracking in whatever the topping is there. So what they do is they bash holes, literally with a sledgehammer, into that hollow core, and then they lay rebar across that joint, and then they fill it with grout. So a lot of the times, most of those crossing every beam line is filled with grout. So you don't often get that kind of clear flow through of cores. We also have pre-tensioned strands in concrete. So what we do is we actually pull on cables in the hollow core that are cast into it to kind of help deal with some stiffness issues in our hollow core. So it makes renovations quite hard with hollow core. If you want to put plumbing, if you've got a toilet right here and you want to put a plumbing pipe right there, well, you can't cut that core because now you've got, or cut that strand, because now you've got a problem. You're cutting through a structural strand in it. So openings need to be very well coordinated in the kind of shop drawing phase on hollow core. Precast, a precast tee. You can see this being brought in to site here. I'm going to add just the term precast to the slide for you guys. Not that common in anything I've worked with. Not common in Toronto at all. I'm sure it's probably more common in maybe in the south. I'm not sure. Not great in seismic zones, I would imagine. But it can be built with precast tees and columns. You can build a whole building in precast elements. You can have double T's and single T's. Here is a double T being brought in, where the double pieces actually start to connect to each other and form your slab at the same time they form your beams. Here's one where they've taken the concept of hollow core and made it work in both directions. So these are bubbles being put into here with rebar laid in it. So what they do is they actually make precast panels as the bottom element. They put balls on it with rebar top and bottom, bring them to site as basically preformed elements, put them in place, and then they cast concrete on top of it. What's really nice is you get a beautiful precast finish at the bottom. So instead of being cast against wood and plywood or reused wood, it's beautiful flat steel. So highly, highly polished finish. Very nice finish. You've gotten rid of a bunch of the concrete weight. So you've really lowered your weight and made all of the concrete be where it's working the hardest. The problem is what do you do at joints and corners and awkward spots? So it works really well in kind of very kind of regular layouts. You can make it work in irregular layouts, which is what they did at One Spadina. So bubble deck was used at One Spadina. You end up with, in awkward spots, maybe not having the voids and having more concrete. So you have to be really kind of smart about knowing when and where you will have full depth concrete, because it adds weight back into the system. Here's a cool precast unit, like this whole thing precast brought to site. Tilt up, not that common here in Ontario, but where I'm from in Nova Scotia, it's quite popular. So you come in, you cast the slab, and now you've got a beautiful, clean surface that you can cast on. They lay a bond break down, cast the wall, let it cure, and they cast in these tabs with columns, and then they get a crane and they hoist it into place and prop it up until everything's in place, and then it stabilizes against itself, and they can start to take these braces off. You can have all kinds of different precast products. More precast products with columns. Concrete walls. We're going to see concrete walls come more into play next week when we talk about lateral load resisting systems. So you're going to see this slide again. A concrete core. So the whole core that has our elevators and our stairwells in it. Often, no matter what the building, it will be concrete, simply because it's a great fire rating. It's easy to build. You can build it independent and then come in and do the rest of the structure. We don't like to intermingle materials because we have different trades on site trying to work together. The core tends to be a little bit different because it can be built almost as its own little structure for several stories, and then the rest of the structure can come in and connect to it. Here's a concrete portal frame. Basically a moment frame, and we're going to talk about moment frames versus braced frames. Not next week, but the week after. We're going to talk about lateral load resisting systems. And so I wanted to show you what concrete looks like while they're making it, essentially. So here is two concrete footings side by side. We've got dowels coming up. They'll have more reinforcing that goes beside this. You can see they've already started to backfill around this one. Here's the formwork that they're going to use to form that footing, and then they'll take that formwork away and start to backfill around it as well. You can see that they have ties there that hold the steel in place, and it's also good for cracking, and we'll talk about that next week when we look at our reinforcing very explicitly. But in case some of the concrete gets here, they've put the first few in already. Here's a rebar slab. Here's little chunks holding it up off the surface so that the rebar is laid out nicely. You can see that if you are the person checking to see that the rebar is laid out at 15 M's at 300 millimeters bottom each way, Well, great, you can measure right here and make sure that that's 300. But you have to make sure that's 300 and make sure that's 300. So coming in and checking that the rebar is put in place. And the rebar is probably being laid on site by the cheapest person on the site. And they might not understand the implications of 300 being really 300. You need those to be 12 inches apart. That's not to say that they aren't smart. It's just saying that they might not know that that's the important part, why it is so important. And you can see here in this picture really where quality control can start to be difficult. You can see reinforcing here for what look to be major columns that are coming in. We've got plumbing. We can see where our beams are being formed here. We can see our slab reinforcing going in both directions. This looks like it's a one-way slab going in that direction, mostly because I can see a beam there and a beam here, but this looks like it's starting to be more than twice the dimension of that distance there. Here is basically a kind of close-up view of what the rebar in a beam might look like. The top steel, the bottom steel, and the stirrups or the ties, we often call them stirrups in the beam. So we would have, this might be 4 20Ms top, 4 20Ms bottom, and 10Ms at 100 millimeters down the length of the beam. Here is column reinforcing meeting a footing. This says slab, but it very much looks like it's a footing. I'm going to fix that too. 46. Footing, not a slab. But it would look very similar if it was meeting the slab as well. Here's some formwork. This is some foundation formwork. You can see that they've got the outside piece on and the inside piece. The engineer needs to be able to review the reinforcing. So the timing is critical of the engineer reviewing this. The formwork, outside formwork needs to be up, holding that rebar in place. But the inside formwork can't be up yet. I have been called to site to do a rebar review, and it looks like this. I'm like, guys, that doesn't help anyone at all. I can't review that. So making sure your contractor understands when reviews need to happen is very, very, very important. Here are some more walls getting ready to be cast. You can see that the rebar needs to keep going up past because it has to lap with the next spot. If you just stop it like this and start it again, well, you have a weak joint there. There's nothing connecting those. So what we do is we lap our reinforcing. You can see here there's formwork starting to come down around cast concrete. You can see these are cast in for connections of some sort. Here's the plywood getting ready to be used as a formwork. Here are the underside of some formwork. Look at this, the concrete and the formwork don't work by themselves for a while. Until that concrete is cured, you need shoring underneath here to support all that. I'm going to add the word shoring in there. I'm finding all kinds of stuff to add to this slide, these slides. So here's some plywood formwork with shoring. We've got the floor slab. Look at this. This is where the beam is going to be to stop the concrete from kind of squishing out the formwork here, because remember that fluid wants to go that way when it's liquid. They have little kickers here. They have temporary beams with shoring, and then they have something to spread the load out so that it doesn't damage what's below it. So all of this is designed by the contractor. The stuff that goes in it is designed by the base building engineer. So here is a series of floors where they have formed a floor somewhere down here. You can see that they have that formwork there. This formwork is being taken out here and brought up and being brought up here to be used in the next layer of formwork. When I started working, plywood forms were the norm. A company kind of came on the market early in my career called Perryforms. I'm sure they'd been around longer, but you went from never seeing them on projects to them being used all the time. Basically, they're engineered formwork systems. So they're a distributor that rather than the contractor, cobbling together plywood and having an engineer design it, it's a kind of a prefab formwork system. You can do really cool things. This looks like it's a curved wall being formed. You can have very refined formwork. You can see that this is a fiberglass for round formwork. You can have concrete sonotubes where maybe you peel them away afterwards. You can, because concrete reads what its formwork is very strongly, you can actually even get words dyed into the concrete depending on what your formwork was. But it will read the features of your formwork. You can get into fancy formwork or custom formwork. So, you've probably all heard of board formed concrete. Well, literally, instead of plywood, they've taken boards and formed it. It is a process. I'd often recommend that your contractor, if they haven't done it before, build a mock-up and test it, because how they put the kind of bond break, how it bleeds through, you want to be in very good control over that so that you have a pre-look at what that contractor's capable of. Insulated concrete formwork. So you can see here, if we need to have something insulated, why not build them into each other, where then your insulation becomes part of your permanent formwork. So you can see here that concrete gets put in here and that this is insulation on the outside. It comes in blocks and kind of gets assembled, and then we fill it with concrete. One of the big problems with this is flowability, and you'll see in the next slide that it's kind of littered with stuff that makes it hard for the concrete to get down to the bottom. One of the things that I've found is that if you come and take basically a pencil and poke it in the bottom of the foamwork here, it'll go right through. So honeycombing, meaning that the concrete hasn't gotten all the way down to where it needs to be structurally, can be a problem. So here you can see that we have insulated concrete formwork here, and you can see what I'm talking about with this being littered with more things than it needs to be. But these are built to accept whatever rebar we need. They're trying to pre-anticipate what layout of formwork we might need. Here's concrete being placed. You can see it comes in its liquid form, put over the reinforcing, and then they smooth it out or they vibrate it and then smooth it out and trowel it. So you can see here coming in its liquid form. I always find this, it looks freakish and alien, that this is the concrete being pumped all the way over to here. I don't even know, this seems to defy the laws of physics to me. Or they'll dump it into these and it'll swing over on a crane and dump it in the location it needs to be. Here they are finishing concrete. Load-bearing block walls often still have grout in them. So this is rebar, and any place there's rebar, that will be filled with, basically, grout is almost like concrete without the aggregate in it. So instead of chunks of rock, it's just the limestone, the sand, and the water mixed together. Here's a non-load-bearing block wall. So it needs to be braced at the top in some way. This is a project I did with a non-load-bearing block wall. Look at these. They actually formed special blocks that have planters in it, and further up this wall, they actually turned blocks on their side. So I really had to control where the rebar was in this. So there are certain cores that are very clearly laid out to make it look random visually, but it's not. Here is the detail of the non-load-bearing block wall top. So you can see that this is a compressible material, so that deck can go up and down, but it won't put load on the block, but it stops the block wall from tipping over. 5, I think, there was actually a death in an elementary school where a contractor hadn't put this on a non-load bearing block wall. They hadn't braced the top, and the non-load bearing block wall fell over. So it seems like a small thing, but it's a critical thing in a project for a non-load bearing block wall. You can have masonry, columns, and piers. And concrete is kind of a unique thing that the material science behind it, we're getting better at as we're making cooler and cooler things. We can incorporate it into our concrete. So here you can see this is translucent concrete. You can imagine by controlling the silica amount in the sand, you could start to do really, really cool things. So you should know rebar rolls, the concrete properties, advantages and disadvantages, basic applications, and the sizing guidelines. Next week we're going to talk about design in concrete, and we're going to spend a lot of time focused on not just the design but also composite. So next week we're going to spend the first half of the lecture talking about composite materials, and then we're going to look at the star of composite materials, which is our reinforced concrete. So hopefully this was a nice light intro back after your week-long break. Have a good week, team.